Okay, welcome back everyone. Today we're going to work out the kind of last bits for doing derivations in predicate logic, or at least the last main bits. I think I got one more kind of obscure, not super helpful rule to introduce next week, but this is the main stuff. The main elements are going to be in place. By the end of today, you'll have all of the main moving parts for doing these derivations. So let's get into it. We're going to do universal derivations, and we're going to do quantifier negation. Okay, so to review from last time, we've got rules for eliminating an existential. So you start from an existential statement and go to a statement that doesn't have the quantifier, EI. We introduce an existential using EG. We eliminate a universal using UI. And then you might be wondering, how do we introduce a universal statement? How do you get a universal? That's what we're going to do today. We need something new to introduce a universal. We're not actually going to introduce these with a rule, however. It's not exactly a rule. It's a new type of derivation, just like direct derivation, indirect derivation, conditional derivation. So you're used to this idea of introducing something with a derivation type, because that's what a conditional derivation is. That's our introduction rule for conditionals. You start with something that's not a conditional, and once you're done your subderivation, you end up with something that is a conditional using CD. So it's just the same sort of thing, except we're going to introduce universally quantified sentences using universal derivations. Okay, so here's the method in general. Here's the intuitive version of the method for showing that a universal statement is true. You show that it holds for any arbitrary object. We talked about arbitrariness last time. So in this case, arbitrary means it cannot have occurred free anywhere in the derivation available from the show line or in a premise cited in such a line. So that's our definition of arbitrariness here. You notice there's very slightly different definitions of arbitrariness for the different parts. And these definitions of arbitrariness are, strictly speaking, stronger than they need to be. So they rule out some things that don't, strictly speaking, need to be ruled out. But we've given you these just because they're kind of, amazingly, these are the simple, intuitive versions of these rules. They're easy versions to work with that are certain to get it right in all the important cases. Okay, so a universal derivation, we say, okay, for any arbitrary object, let's call it x, such and such holds. And if you've shown that it holds for any arbitrary object, then you've shown that it holds for all objects. Therefore, for all x, blah, 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 blah. That's the intuitive version of this. So you're going to start from something that's basically a free variable and end up with a bound variable. I'd just like to register a complaint with the gods of logic that this is a counterintuitive way of thinking about this thing. So a bound variable, a variable bound to a quantifier, is in some sense easy to change. Because it doesn't, for all x, fx, then gx, is saying exactly the same thing as for all y, fy, then gy. And next week I'm going to introduce a rule called alphabetic variance that lets you go from one to the other. So if you got for all x, if fx, then gx, then you can just replace all instances of the variable with some other variable. And it means exactly the same thing, right? You're able to instantiate all the same things. That bound variable is in some sense very free. And a free variable is in some sense quite fixed. Because remember what we're doing with free variables. Remember from last class, we talked about free variables as kind of a pseudo-name, a quasi-name. Like if you say, somebody burned down the house, let's call them x, and then you try to gather information about x, right? You're not allowed to change the name of x to y then, right? There's a difference between if you say, well, we'll just call them x for the time being until we figure them out, figure out who it is, and then gather information about that person, and x stands as like a kind of pseudo-name, a quasi-name. But you can't just flip that for some other quasi-name, right? You're not allowed to swap between quasi-names, between the free variables. So in some sense, once you've used a free variable, once you know something about, so in this last line it says fx, x is appearing free. We know that x has the property f, so we know something about x. We've gained information about it. So you can't just swap x out for some other thing. So my complaint is the following. This is just, I'm literally just complaining to you right now. A free variable is fixed, and a bound variable is free. It's annoying, but that's just the way logicians speak. So anyway, the thing to remember here is that once, and this is why we have this rule about arbitrariness with universal derivation. So we want to show that some property, some sentence holds for any arbitrary variable. That means we need to use a fresh variable, because if it has appeared free in a previous line, then we have information about it, right? We've fixed that information to that pseudoname, and so it's no longer arbitrary. We need to go from some fact about a free variable to a bound variable to a universally quantified sentence. We need it for it to be true regardless of anything that we know about it. We can't be relying on any prior information that we have about x. Otherwise, we can't infer that it holds for all x. So that's why this rule exists. That's why it can't appear free in any previous line or any premise cited in the previous line, because that's having information about the free variable. It's fixing information about the supposedly free variable. Okay. Okay, so my complaints aside, because of this arbitrariness stuff, here's a derivation strategy thing to keep in mind. If you got a universal you need to show, you write a show line for it as soon as you can, right off the bat, because that's how you preserve the arbitrariness of the variable that you're dealing with. I don't think this is ever going to come up in this course, but now I've told you two things that are potentially contradictory. One, if you have an existential, you should instantiate it right away. And two, that if you need a universal, you should write a show line for it right away. And what happens if you have both? Then I recommend that you choose wisely, with great insight. And that's about all I can tell you, because there's not going to be a general rule here. Again, I would worry more about this if this situation was going to come up a lot in this course. I really don't think it's ever going to come up in this course. So don't worry too much about it. If it does come up, you'll have to just work it out from context. But is that okay so far? Okay. Probably the best way of going about this is just showing you examples, yeah? Examples are always more helpful than just me standing here describing the overall situation. So let's do that. Okay, not this one. Here we go. Okay. So the conclusion of this derivation is a universal for all x, fx. So of course, we're going to do the usual thing. We're going to say, we want to show that. Show for all x, fx. Okay. So the thing that previously we had some automatic rules about what you do with a given show line. If it's a conditional, start a conditional derivation. If it's not a conditional, start an indirect derivation. We're going to add one more step to that decision tree today. So if it's a conditional, start a conditional derivation. If it's a universal, start a universal derivation. Okay, so what do I do to do a universal derivation? Here's what. I want to show an instance. I want to show fx. So that's just an instance of the thing I'm trying to show above. Okay, and does it satisfy our definition of arbitrariness? Our definition of arbitrariness says it doesn't appear on any previous line, on any available line, and it doesn't appear in a premise free cited. It doesn't appear free in a premise cited on an available line. So neither of those two things have happened. So far, fx is purely arbitrary. We know nothing about x so far. So now we just have to show fx, and then we will have achieved our goal of showing that it holds for all x, fx holds for any arbitrary x, and we can close off our universal derivation. Okay. All right, we might as well assume ID on this. We've got a show line. It's neither a conditional nor a universal, so I'm going to assume ID on it. Okay. Now what? Now what? We have one available line, two premises. Our two premises are, helpfully, existentials. We've got a rule about what to do when we have an existential. We instantiate it, right? Instantiate it right away. So let's do that. We'll instantiate, let's do this one first. It doesn't really matter which order you instantiate them. Oh, wait. I got ahead of myself. Not fi. That should be not fx. Come on, you're supposed to call me out on these things. When I do foolish things, I'm relying on you to publicly embarrass me. Come on. Okay. Okay. So, all right. So we are going to instantiate these. I'm going to do premise 2 first. So premise 2, ei. And I don't have to think about what I'm going to ei this to. It just has to be something I haven't seen before in the proof. So I do have to think about it in terms of not using something I've seen before, but that's really it. Okay. And I have written this question out wrong. I have written this question out wrong. One of those should be a y in the first premise here. My apologies. And I can't remember which one it's supposed to be. Can't remember which one it's supposed to be. I might get halfway through this and find it unsolvable. All right, I'm going to call that one y. My apologies. Okay. Here we go. Let's see if I can solve this. And if I can't solve it, either I'm bad at derivations, possible, or I chose the wrong one. Okay. Okay. All right, so nonetheless, I've existentially instantiated this one, which means it's in some sense used up. Like I probably not going to use it to existentially instantiate to something else again. Now this is also an existential, so I also want to existentially instantiate it to something. Yeah? Oh, I bet I did this wrong. Oh, God. All right, well, we'll try it. The problem is I don't have it written down what it's supposed to be anywhere. So, no, I bet I did it. I bet it's supposed to be there exists an x such that for all y. Boy, I hope that's what it is. No, no, no. You're witnessing your prof have a crisis of confidence right in front of you. Okay. Okay, let's just try it and see how it goes. The important lesson for today is that it's okay to make mistakes. Okay, premise 1, ei. And again, I don't really have much choice about what I'm going to ei this to. All I know is that I have to existentially instantiate this thing to something, and I'm not allowed to existentially instantiate it to I. I would love to be allowed to existentially instantiate this thing to I. That would make my life so much easier, but I'm not, because I has appeared free in the proof already. So I'm going to ei this thing. So for all x, if fx, biconditional fj. That's what I got to do with this thing. Okay. Now I've got if fx then fj. Fine, fine. So I can universally instantiate line 5. So 5 ui gives me, let's say, if fx biconditional fj. So all I did there was instantiate this x to x, if fx then fj. Yeah? That's okay? Oh, you know what I should have done, though? You know what I should have done, though? I should instantiate this to I. That's what I should have done. That's okay. You're allowed to existentially or universally instantiate as many times as you want. So 5 UI. Okay. Now, yeah. I think I might have needed both of those, actually. So I'm going to pull out one half of this biconditional, fj, so 7 biconditional to conditional. And then I've got fi on 4 and fi then fj on 8. So I say 4, 8 modus ponens, giving me fj. Ooh, I did need both sides. You can tell I don't remember how to do this. So on line 6, biconditional to conditional, giving me if fj, then fx. Oh. 9, 10 modus ponens, giving me fx. Hooray. That's the thing I was trying to show. Direct derivation. Okay. So I wrote it okay. It turns out the way I decided to assign x and y there worked out okay. Any questions so far? Just about that part. Yeah.
I thought you couldn't universally instantiate to F5.
No.
It's already there, but then you did.
No, you're allowed to universally instantiate to anything at any point.
Just you can't existentially.
That's right. That's right. So the restrictions are on what you can existentially instantiate to. That and the no capturing rule. So if there was another quantifier inside that, then I'm not allowed to UI to match that internal quantifier. But universally instantiate, you can instantiate to anything. And in fact, that's how it's going to go most of the time when you've got a mix of universals and existentials. So what I did here was existentially instantiate first, because you have to have something fresh, and then universally instantiate to match the thing that I existentially instantiated to. Right? So I EI'd to I, and then I UI to I, because then I can use that thing that I EI'd to in conjunction with whatever I UI'd to. So that's not just allowed, it's actually generally a good idea strategy-wise. So you EI to something random, and then you UI to match the EI. So that's what you did, that's what I did there. And notice, it turned out to be important. I thought I was messing it up, but that's just because I was frazzled. It turned out to be important to UI line 5 twice. I needed both of those biconditionals to get first from fi to fj, and then from fj to fx. So you can universally instantiate a number of times from a universal, and sometimes that's not only allowed and helpful, but actually necessary. Okay. So if how I got that far is okay, now I'm going to close off the universal derivation. So on line 12, I'm going to say the following. Line 2, UD. Universal derivation. So I showed fx, which is a perfectly arbitrary, we said at this point, x is a perfectly arbitrary variable. I showed for a perfectly arbitrary variable that fx, therefore, for all x, fx. Box and cancel. Okay, so now we've introduced a universal with some fumbling and a mild sense of panic. Yeah?
Line 11 is not indirect derivation?
I could have said indirect derivation if I'd cited line 3, but it's also exactly what I was going for. So you can do, this is a mixed derivation, but it's fine to, because it's the thing that matches the show line exactly, it's okay to call it a direct derivation. Yeah, either would have been fine. Yeah. Other questions about this? You want to see another example? Okay, let's do another one. just pray that I wrote it out right. Okay. Once again, our job is to show a universal. We're going to show for all z dx. I'm sure that's supposed to be a z. I'm actually confident this time. Okay. So, we've written a show line for a universal. If you've written a show line for a universal, the thing to do is start a universal derivation. So, we just write out an exact match for the thing that we want to show, so that whatever is in the brackets. So I write a second show line. Crucially, I write a second show line. It says dz, then az. By the way, on Logic 2010, please don't write this when you're writing out your derivations by hand, because it just shows me that you don't understand what a show line means. But on Logic 2010, the command to do this is show inst, show an instance. So if the last show line you wrote is a universal, you just type show inst, and it'll generate an instance of that universal. But again, please don't write that on your test. It makes me feel like a failure that you don't understand what a show line is, that it doesn't need to be justified. Okay. Okay. So we've started a universal derivation. We wrote a show line for our universal, and now we're going to try to show an instance of it that's totally arbitrary. So now it's just a matter of trying to show this conditional. What do we do when we have a show line for a conditional? We start a conditional derivation. Same old, so again, there's a decision tree. When you look at the show line, what should I do now? Trying to show universal, start a UD. Trying to show a conditional, start a CD. Anything else, start an ID. So we're going to assume this for conditional derivation and try to show on that basis AZ. As a matter of fact, I know that I don't need the ID, assume ID, so I'm not going to do it. But all we have to do is show AZ, and we can close off that conditional derivation, and then close off the show instance, and then close off the universal derivation. It's not too hard to get there now. It's not too challenging, given what we've got. What we've got are just line 3 and these two, and premise 1 and premise 2. But those are enough to get us to the finish line. So we're just going to start universally instantiating these things. Yeah? So if you have a universal, probably the thing to do with it, unless it's the antecedent of something or you can build the negation of the consequent, probably the thing to do is to universally instantiate it, to get at the parts of the whatever's in the bracket, right? So premise 1, let's universally instantiate it. And what are we going to universally instantiate? So now you have to make choices. When you're using UI, you can UI it to anything that you want, generally speaking. So you have to think about what you're going to UI it to. Unlike EI, which is you're forced to just do something totally new, UI is kind of the opposite. You want to do it to something that you already have some information about. In this case, the only thing that we have information about is Z. That appears already in my proof. It also appears in premise 1, so I'm going to UI premise 1 to Z. If dz, then mz. And let's do premise 2 as well, just same thing. We're going to UI that. If mz, then az. Hopefully your good old predicate logic moves are flooding back to you now, and you can see the finish line from here. So we're just going to say 3 repeat, 5 modus ponens, giving us mz. then 6, 7 modus ponens, AZ. And hey, that's the thing we were trying to show. Show AZ, we showed AZ, so on line 8, we did a direct derivation. And why were we trying to show AZ? Part of a conditional derivation. So we assumed dz, we showed AZ on that basis. So on line 2, we did a conditional derivation. Okay. And finally, why were we trying to show that? Because that's a purely arbitrary instance of the universal that we were trying to show in the first place. And since we showed a purely arbitrary instance, what we showed is that for anything, if D, then that thing, then A, that thing. If it has the property D, then it has the property A. So on line, sorry, I gave the wrong line here. This should be 8, we did a direct derivation. 4, we did a conditional derivation. Sorry. That's because 2 is where we did a universal derivation. Okay. How's that? Okay. I mean, if this is going down okay, like if you're feeling reasonably comfortable with this, then you've pretty much got all of the skills for derivations in predicate logic. I got one more thing to show you, but it's quantifier negation. We've been talking about it for the last little while, so it's not going to be, that one is fairly straightforward. Yeah? Questions about this? Feel okay about it? Okay. So let's talk about quantifier negation for a bit, and then we'll come back and maybe do a few more examples. Okay. Oh yeah, sorry, I had one more thing to say about this. I want to share a moment of horror and terror with you, because I don't like to be alone with that kind of thing. So here's that derivation that we just did. It's straight from the textbook. And I had a heck of a time figuring out why their version is okay. So their version is slightly different than mine. And I was like, that can't be right. That can't be right. I almost wrote to the textbook people and said, you screwed this up, you guys. Because here's what I thought. So look what they've done here. They've got the show line for the universal, and then they universally instantiate to Z. And I thought, well, doesn't that mean that when you start the show line number on line 4, that it's no longer arbitrary, because it has appeared free on a previous line? I thought, no, that can't be right. And I beat my head against the wall for some time, until I worked out that what they mean is the following. So to clarify what they mean by hasn't appeared free before the show line, that's ambiguous between the show line on line 1, the show line for the universal, versus the show line for the instance. Right? So this is okay because Z does not appear free before the show line for the universal. They did the show line for the universal on line 1, so it doesn't appear before that and has not been cited before that. So when they say it's not allowed to appear free before the show line, what they mean is the show line for the universal, not the show line for the instance. So there's a universal derivation involves 2 show lines, one for the universal, one for the instance. The arbitrariness requirement is that it can't appear free before the first show line, the one for the universal. Okay? I was deeply disturbed by this, deeply disturbed. It took me a while to get undisturbed. Okay? I mean, I'm not going to give you all that many. There'll probably be a few, but there's not going to be all that many universal derivations that you have to start that aren't like so if the conclusion of the argument is the universal you're trying to show, you just start the universal derivation right away, and the arbitrariness stuff is you really don't have to worry about it because you just started it right away. So typically that's what you'll be facing. If you have to start a universal derivation halfway through a derivation as a subderivation, then you have to think a little bit about what's arbitrary, but generally speaking, it'll just be the first one that you have. It'll be the conclusion of the argument rather than some sub-premise you have to work out. Okay, so don't get tripped up on that. Okay, just one last thing then. Quantifier negation. So this is in fact a derived rule in predicate logic, but it's not one that you have to unlock, I believe. Has anybody used quantifier negation in Logic 2010? Yeah, and you didn't have to solve anything? Okay, so yeah, this is a derived rule, but standardly it comes unlocked, so you don't have to do the thing like with our old derived rules. But it's a derived rule because there is a theorem that you can solve in Logic 2010 where you don't use you get the result of quantifier negation without using it, which makes it a derived rule. Okay. But basically, it works as follows. It lets us switch between universals and existentials. Here's all 8 versions of it. There you go. This is in your textbook. There's no need to write this down. It's also on the slides that I posted. But I hope the pattern is clear. So it's very unlikely that you'll have to memorize all these. Just understand the pattern of them. Just understand the pattern of them, where you either move a negation from outside the universal, flip the quantifier, so you always flip the quantifier and move the negation, basically. If both the quantifier and the thing after the quantifier are negated, flipping the negation means dropping both of them. If neither are negated, it means adding both of them. Yeah? Is the pattern clear? Like, honestly, when I'm solving these things, I only ever use quantifier negation on a negated quantifier. Those are the only instances. So really, these 4, the leftmost 4, are the only ones that I ever use it on. Feel free to memorize and help yourself to using them all if you prefer, but really quantifier negation is useful for, like, the typical case where it's useful is where you've got a show line for a quantifier, you assume ID on it, and then you can do something with that negated quantifier. You can turn it into something that you can use. So that's the most common place to use them. Those are the ones I would worry about most. Yeah? Okay. So I feel like we've gone through this stuff. Would you like me to go through and try to work out the equivalences between these? Or does that feel, I'm seeing people shake their heads. Like, if the equivalences between these are unclear to you, I guess the thing to do would be to spend some time with these slides and think about them. Think about how they're saying the equivalent things, yeah? That's what I would recommend. Using quantifier negation in practice, you don't need to deeply understand it, but it helps. Okay, let's just do some more examples then. We'll take whatever time, we got 13 minutes, 15 minutes left or so. Let's just do some more examples. I think that's more helpful than trying to get deep into this stuff. Do you agree? Okay, more examples. Okay, so these are going to be slightly longer. They're going to be more complex predicate logic derivations that we've done so far, but we'll get through it. So we're going to show this thing. If there exists an x such that jx, then there exists an x such that gx and jx. jx, that is an x. Whoa. Oh, please don't do that. Please stop flashing cursor. Okay. Okay. So we've got a show line for a conditional. That means we start a conditional derivation. So we're going to assume there exists an x such that jx, and going to, on that basis, show that there exists an x such that gx and jx. Okay. So before, when we were doing these, I said, this negated thing wouldn't be any use to us, so I'm not going to do the assume ID. But now we have quantifier negation, and that negated existential could potentially be useful to us. So let's do an assume ID here. So it's not the case that there exists an x such that gx and jx. That's assume ID. Okay. Now, as it stands, a negated existential isn't very useful. You're certainly not allowed to existentially instantiate it, for example. You're allowed to EI an existential, not a negation of something, which is what that is. But we can turn this into something useful using quantifier negation. We can say, for all x, it's not the case that gx and jx for quantifier negation. So this one says there's nothing that's both g and j. And this says, for everything, it's not the case that g and j. Yeah? Yeah? OK. Right. OK, now let's take a breath, survey our resources, see what we got, see where we're going. OK. So far, we've got, so what do we got? We get these premises. This one's a disjunction, so we'd have to build the negation of one half of it to make anything out of it. This one's a universal, so I can use that whenever I want. Line 2 is an existential. That's something we should do something with right away. Yeah? We've got an existential. You should do something with it. So let's existentially instantiate it. 2 EI. What am I going to existentially instantiate it to? Should I do a careful survey of my resources? Yeah. Want I have to what? Oh, yes, thank you. Thank you. Sorry. 2 repeats. EI. Yes. Thank you very much. Right. So what am I going to EI? What do I EI this to? Literally just anything that I haven't seen before. You do not have to think about what to EI to. So let's call it ji. OK. So now I'm going to start, now that I've existentially instantiated, I'm going to start UIing things to match that, to see if I can get anything useful out of that. So, let's UI line 5. So the thing to do really is to look for matching predicate letters, right? So I could UI this premise to I, but it doesn't match j, right? So there's no j in here, which means I can't really do anything with the ji that I have. So I just acquired a free variable, ji. Can't really do much with it if there's no j in here. There's a j in here. That would be nice. That would be nice to do something with, but I've got to build the negation of one or the other of these. So I don't want to deal with that just yet. Let's universally instantiate this thing, because j does appear here. So line 5, this is just why I'm choosing to UI this thing. I'm going to UI this, so it's just everything that happens after the bracket and just dropping i's into both of those. So what we get is it's not the case that gi and ji. Yeah? Is it clear why the UI works that way? It's just when you're UIing, it's just whatever happens after the quantifier and then replacing every instance of the bound variable. OK, let's open up 7 using De Morgan's. 7 dm, that gives us not gi or not ji. OK? Potentially helpful, because I got ji here, and this is not ji. So let's say line 6, double negation, line 8 MTP. That gives us not GI. So far, so good? Feeling okay about that? Okay. Okay, so we've got, what do we got? We got useful looking lines right now include line 6, JI, that looks pretty good. Line 9, that looks pretty useful too. But I've kind of run out of moves in some sense. Not really obvious what to do. So I used this, I've used, you know, this line. I used this line by turning it into line 5. I used this line by doing all this stuff. So, feeling a bit stuck now. Feeling a bit stuck. Feel like I don't know what to do. However, I noticed that premise 1 looks like it's got the right materials to get us from, so there's J and G here, and F and H here, and there's F and H here. And I've got J and G. So I've got a whole bunch of J stuff and G stuff. So maybe I can build the negation of this to get this, and then that'll help me to get this stuff. Does that make sense? What I'm trying to do here? Okay. So I'm going to write a new show line. The last refuge of the stuck deriver. I'm going to show for all x. Sorry, no, I'm going to show the negation of that. Yeah, so I'm going to try to show it's not the case that for all x, if jx, then gx. Sorry, we got to back up here. Still good? Okay. Okay, so remember how I told you that if you got a show line for a universal, you start a universal derivation? But this is not a universal. This is a negation. So the thing to do here is actually just to assume ID on it. So we're going to assume for all x, if jx, then, oh wow, gx. Actually, do you mind if I'm going to zoom back in? This is, writing is too small. Okay. Yeah, look how clunky that is. All right. And that's an assume ID. And then we can use that line to try to generate a contradiction. So I'm going to universally instantiate line 11 to I to give if ji, then gi. I got ji, so 6 repeat 12 modus ponens gives us gi. I've got not gi, so I can say 14, I can say 9 repeat 13 ID, closing off this subderivation. Okay, so why was I doing that? Why was I attempting to close off that subderivation? The point of that was to build one half of this. So now I can say the following. I can say, I'll start again up here if you don't mind. Sorry, this is, I do have to zoom out. I'm just going to have to write carefully. Okay. So on line 15, we're going to say the following. We're going to say we got line 10 in premise 1, MTP, giving us there exists an x such that fx and hx. Okay. Now what do we do with that? Well, it's an existential, so we need to instantiate it right away. You know what I wish I could instantiate this to? I. That would be convenient for me, because I have a whole bunch of stuff with I in it. But I'm not allowed to do that, because that would be violating our requirement that we have a fresh variable. So I'm going to instantiate it to just Same thing I always instantiate it to, something I've never seen before. Let's say J. So Fj and Hj, that is line 15 EI. Okay. But now we can UI things to match J, right? What do we got? We got if fx then not hx. Let's UI that. So premise 2 UI, we're going to say if fj then not hj. And if you're sharp on your predicate logic stuff or sentential logic stuff, you can smell a contradiction coming. You can just smell it. So 16, simplify, 17, modus ponens. Simplifying off this fj, feeding it into here, we get not hj. And 16, simplify, 18, id. Simplify off this hj, we get not hj, and we've done it. So that closes off this show line. And having closed off that show line, we can at long last say line 3, conditional derivation. Quick questions about that? Okay, so it's getting more complicated. It's getting more complicated, but don't panic. You've got all the bits and pieces. You understand all of the bits and pieces of this proof. Now you just need practice. Okay, thanks everyone.